All right, so these are some notes to cover how to name and write formulas of compounds. This is all stuff that you should have learned in honors, except for a very small portion about hydrates at the very end of page 11. There is a flowchart on page 12 that kind of recaps and kind of puts in some of the questions and decisions you need to make, but what I want you to do is just get the examples done on pages 9 through 11 and 13. And if you can do that without this video, it might go quicker. You can always just click through and check your answers with the video or with me in class or tutorials. But this is just in case anyone needs to watch me work through examples of each type. So first of all, remember that compounds are multiple different elements held together by chemical bonds. And there's a general attraction between those atoms to make them form a bond. And there are two general types of bonds that form because of different situations. The first is ionic, where we have a metal and a non-metal, someone that wants to gain electrons, someone that wants to lose electrons, which means they transfer electrons between them, and then they're attracted to each other's opposite charges. Covalent compounds, though, are two or more nonmetals. Each of these nonmetals want to gain electrons, so they kind of fight over those electrons, and then they find a way to lower their shared energy state by sharing these electrons. So they get close enough where their electron orbitals overlap, and they can both have those electrons to fill their octets. So, just a quick note, nomenclature is not something you're going to have a question on directly on the exam. It's just not going to happen. It's too foundational of a skill, but it is a skill that you need to have so that you can understand the questions that they're giving you and not be stuck trying to figure out what chemical is which. So this is something you need to know. This isn't going to be a dedicated question on the test, though. So let's start by talking about covalent compounds. These are the simplest to name. We call covalent compounds molecules when they have formed, and they're held together by sharing electrons, like we already said. Because they share electrons, there's multiple different ways that they can share electrons and multiple different ratios that the same two elements could come together to make a covalent compound. So we use prefixes, which we'll talk about in just a moment, to tell how many of each element are in that specific compound. Now there are two covalent compounds you need to know the common name of, that we might not call nitrogen trihydride. That's ammonia. They're probably going to use the word ammonia. And then, of course, H2O is water. The other thing to be aware of is that there are 7 elements that are diatomic elements that exist in a molecule form, not as separate individual atoms. And so you have these 7 listed out for you here, and I've already gone ahead and put the little 2s on them, and you should be kind of familiar with them. Once again, not going to have a question like which is a diatomic element, but it's something that you should be aware of. That's why certain reactions happen the way that they do. A way to remember those is a little mnemonic device, I bring clay for our new house, where the first letter or 2 letters of each of those words is one of these 7 diatomic elements. Or, honestly, my favorite is shorter, it doesn't make any sense, but the word Brinkelhoff kind of sounds like Hasselhoff. Also takes the symbols of each of these diatomic elements in a slightly different order to put together a silly sounding word. Now, when it comes to naming compounds with different elements, we are going to use these prefixes, mono 1, di 2, etc., in order to label how many of each element we've got in that compound. And you'll notice that oftentimes, sometimes the A or O at the end of this prefix is dropped if it's doubled up at the beginning of the next element's name, like tetraarsenic might just be tetrarsenic, or octaoxide, or especially like monooxide. We just write monoxide there. And also on the note of that mono prefix, there we go, now you can actually read it, we do not put the mono prefix on the first element. There are lots and lots of compounds that just have one of the first element in their formula, so we don't want to start, a majority of our compound names with mono. It's understood if we say carbon dioxide, even though we don't say monocarbon dioxide, that just saying carbon there at the beginning means there's just one of them. We do still use the mono prefix on the second element, but we do not use it on the first element. So going through these examples here, we'll start by decoding our names into formulas, which I think is a little easier because we just have to focus on our prefixes and their meanings and then figuring out what these elements are here. So diphosphorus means we have 2 phosphorus atoms. Remember that that prefix goes ahead of the name, but the little 2 is going to go after phosphorus's symbol. Trioxide, we have 3 oxygens, so P2O3 is our formula. Carbon is C. Tetrachloride means I have chlorine, and it has 4 there because tetra does mean 4. Dinitrogen means I have 2 nitrogens. Pentoxide, notice they dropped that vowel there. It's not pentaoxide. So we do have oxygen there, and penta means we have 5 of them. Very similar name in number 4, dinitrogen means we're still starting with 2 nitrogens. Then trioxide is going to have 3 oxygens there. Like I said before, multiple different compounds with the same elements that have different ratios. Ionic is not going to be like this. 2 elements are only going to get 1 correct formula, and that's all we need. Now writing names, focus on the prefix first because that always goes first. So 3 is tri, P is phosphorus, and then I have 8 oxygens, so that's going to be octaoxide. Remember that we changed that element's name to have "ide" to show it's part of a compound. I think we've seen this before where it's just octaoxide or octoxide. It's not something that the graders will count off for because, once again, you're not going to have dedicated questions just about this naming, so you more need to recognize why other people might drop a vowel, whether you drop it or whether you don't when you're talking, writing a free response or something about that. It's not going to affect your score one way or the other. So do whatever seems right to you. Try saying it out loud and what seems more natural. This next one, we've got 2 chlorines, so that's going to be dichlorine. And then 7 oxygens. 7 is hepta. And we might drop that A for our oxide here. Dichlorine heptoxide. Then we've got tetraarsenic, but I'd probably drop that second A. Tetraarsenic. And then 6 oxygens. Oh, all of these have oxygen at the end of them. That's a pretty common element, but I probably could have done better. There's only one that had a different element there. So 6 is hexa, and then of course oxide. And then 3 phosphoruses means triphosphorus is our starting name. And then once again, we've got 8 oxygen, so octoxide to finish that off. Now, if we move into ionic compounds, there's no superscripts or charges in formulas, even though the atoms have charges when they form these bonds. That's what attracts them together, like we already talked about. The charges are always going to cancel each other out. The total charge of the compound is 0, which is why you will never see a charge written in one of these formulas. The cation, the positive ion, goes first, but when we're going straight from a name to a formula, we just keep everything in the same order. Like we already talked about, transferred electrons, and this is where I wanted to make sure to emphasize. I think I've said this word already once, but a representative particle of an ionic compound is not technically called a molecule. It's called a formula unit. Molecule is only used for covalent compounds. So we're going to start. There's a couple different general types of ionic compounds, and the first one we're going to focus on is binary, meaning there's just 2 elements. So an metal and a nonmetal. The metal name stays the same. The last name of that nonmetal ion is going to change to "ide", just like with covalent. So oxygen changes to oxide, phosphorus, phosphide. We've already seen that. Here, though, I just want to emphasize with something like Na3P, that's just sodium phosphide. Those numbers in our ionic compounds do not become part of the name because there is only one correct formula for when sodium and phosphorus get together. The Na has a +1 charge according to the periodic table, and the phosphorus has a -3. And so in order to add up to 0, we have to have 3 of these +1 charges to cancel out that -3 charge. In honors, what I called this process of canceling out charges was cross, drop, reduce. You can bring each of those charges over and down onto the other element. So Na gets a 3 on it now. P would technically get a 1, but we don't write those 1s there. And that's our formula. If we have something that ends up like just xy2 after we cross and drop, we do need to reduce that down, because if that is a x with a +4 charge and a y with a -2 charge, then all I need in order to get those charges to cancel out is 2 of those y's to cancel out the +4. So we always take the simplest, most reduced form of these ionic compounds when we put those charges together. So cross, drop, reduce. Don't always have to reduce, because most of the time like a 1 and a 3 or a 2 and a 3 won't reduce, but you need to check, especially if they're 2s and 4s. Now, we already talked about the different charges elements can have in the common groups. So group 1 and 2 metals, which are going to be a lot of our ionic compounds, have a +1 and +2 charge respectively. And then we said that those transition metals can have multiple charges, all except for these 3. Aluminum is always a +3, zinc is always a +2, and silver is always a +1. So these guys are kind of normal ionic compounds. If there are any other transition metals in your ionic compound, though, because they can have multiple charges, we need to figure out what charge they have in our specific formula and put that number, whatever their charge is, in parentheses in the middle of the name using a Roman numeral to indicate that charge. So you'll see that first in these examples. We'll practice using the Roman numeral in that iron 3 chloride, and then we'll practice coming up with that Roman numeral and doing a little bit of work in those last few examples to come up with what the Roman numeral should be. But like the sodium phosphide example, when we're writing names, we just name what we see, and sodium is not a transition metal, so that just gets to stay sodium, and then oxygen changes to oxide. Magnesium chloride. In order to write this formula, we need to know the symbols and their charges. Magnesium's in the second column, so it has a +2 charge. Chlorine has a -1. If we cross, drop, reduce, the 2 is going to come over onto the chlorine, and our final formula is going to be MgCl2. Now, same kind of idea with iron 3 chloride. Iron is Fe, chloride is Cl. We do know chlorine's charge, either from the last problem or from the periodic table, but if we look at the periodic table, it doesn't tell us iron's charge. It's one of those weird transition metals, but that's why we have the Roman numeral 3 here. It's telling us iron has a +3 charge. And from here, we just cross, drop, reduce. That 3 is going to come over onto the chlorine. Now, as we're naming this next one, manganese is Mn, and as you're probably checking your periodic table for that, notice it's a transition metal. So we are going to need a Roman numeral, but let's come back to that, because the rest of the name is absolutely normal. S means we're going to end our name in sulfide. But we got to figure out what the charge of manganese is here in this compound in order to put it in as a Roman numeral. And the way we do that is by thinking about the charge we do know. Sulfur is a -2, and I just have one Mn balancing out that one S. So in order to cancel out that -2 charge, Mn must have a +2 charge. So we give that a 2 Roman numeral. This next one, the normal name, actually the next 2, that's lead with oxygen. So it's going to be lead oxide. Actually, both of these are going to be some kind of lead oxide here. But notice that they have slightly different formulas. So the charge of lead in these 2 compounds is going to be slightly different. And just like in that last example with MnS, we've got one Pb balancing out one O, and this time oxygen's charge is the same as sulfur. So if oxygen's a -2 balanced out by a single lead, that means this has to be a lead +2. Here though, when I have 2 oxygens that are each a -2 charge, lead has to be a +4 in order to cancel it out. So that becomes lead 4 oxide.
Now, the other type of ionic compound that you're going to run into are called polyatomic ionic compounds. And like the name implies, polyatomic means many atoms. So these are not binary. These have more than just 2 elements in the compound. Now, we still, because it's ionic, have just a positive and a negative piece, but one of those ions, one of those positive and negative pieces, is going to have more than one atom together. So that's where this list of polyatomic ions comes in, because these are the elements that tend to be held together as a group, sharing electrons. So they're covalently bonded groups of atoms, but they have a few extra or a few less electrons than they would expect from just the normal neutral atoms, which gives the whole group a charge. So the only positively charged polyatomic ion that you're probably going to see is ammonium. All of the rest of them are negative, and I've grouped them up by their charge here. And you do not have to memorize these, but you being familiar with them is going to help in the long run when you're working with things, and recognizing some of these polyatomics and how they move and how they might bond, form new reactions is going to be helpful. We are going to talk about solubility rules. You might have noticed by now that there's no solubility rules written for you on the back of your periodic table like they were in honors. So we are going to have to memorize some simple SNAP solubility rules, which just tells us that sodium, nitrate, ammonium, and potassium are always soluble. That's literally all that we're going to be learning there. So recognizing our nitrate and our ammonium ions will be especially important because those are always soluble. So we'll go into a little bit more detail with that in our Unit 3 equilibrium unit there. But the rest of these, you just kind of need to be able to recognize a little bit. And while we're doing these practice problems in our packet, you can always come back and reference this table. So looking at our practice problems, sorry about that, I've got a couple of slides out of order for a moment. We're going to write these formulas when we're given the name, just like we did with our normal binary ionic compounds. The only difference is that as we're finding our symbols and their charges, sometimes we're going to see a special group. And the best way to tell that it's one of those special groups is that the name ends in ate or ite. We can tell this isn't normal sulfur because if it was, that'd be potassium sulfide. This is potassium sulfate, which means that's that SO4 group with the -2 charge. We're still going to cross, drop, reduce. So the 2 and the 1 are going to switch places, and it becomes K2SO4. The thing to be careful about, there's ammonium and hydroxide. Those are the two polyatomics that do not have that ate ending. But ammonium we really need to get familiar with because it's the only one that's positive, which means it's the only one that can be first in an ionic compound. So we've got that ammonium, and then carbonate. Oh, we've got another polyatomic here. Carbonate is CO3 with a -2 charge. So we are going to cross, drop, reduce these charges, and because we're bringing a number, a subscript, over onto this ammonium, we need to put it in parentheses. We don't generally put these in parentheses when there's just one of them. You're never going to see AP Chemistry at College Board do that. It's not the convention, and it's only when you need more than one of the group that you put them in there. Now, if it helps you, you're trying to balance something, you want to put parentheses around those groups temporarily, sure. It's just going to look weird to any AP graders looking at it. Now, along with these polyatomic groups, we can still have some transition metals mixed in. And I can tell this titanium has a +2 charge because we have that 2 Roman numeral here in the middle. Then hydroxide is an OH group, like the name implies. It's one of those weird ones, like I already said, that doesn't end in ate or ite, but even the name sounds like it has more than one element together. When we cross, drop, reduce that, bringing our 2 over onto the hydroxide, that becomes TiOH2. Now, writing the names, you can tell when you look at these formulas that they have more than one element together, or more than 2 elements together. So one part of this is going to be a special group, and it is going to tend to be the ending 2 elements, unless you see ammonium there at the beginning. The name goes exactly like it did before. No prefixes, just name what you see. Zinc, and then PO3 is phosphite. If you're wondering why there isn't a Roman numeral, zinc is in the middle in that transition metal section, but it always has a +2 charge. So I think our formula here is actually missing a 2 on that phosphite to be fully correct there. My apologies. Same kind of thing happens down here. The special group is that SO3 group. So Ag is silver. No Roman numeral, it always has a +1 charge. And then SO3 is sulfite. Next one, we can definitely tell NO3 is our special group because it's already in parentheses there. So our first name of this is going to be cobalt, and then NO3 is nitrate. And cobalt is a transition metal. It does not have a set charge like zinc and silver do, so we do need to find its Roman numeral. And just like with our binary ionic compounds, let's start by figuring out what is the charge of this thing that is with the cobalt. Well, each of those nitrates has a -1 charge. So if we have 3 nitrates here, according to this number outside the parentheses, that means that the total negative charge in this compound is -3, which must mean cobalt is a +3 to balance that out. Remember, it always has to add up to 0. So, hopefully ionic compounds aren't too hard, and covalent definitely just name what you see, remember those prefixes. Where things get a little bit tricky is acids. So acids are kind of special. They are molecules, which means they are covalently bonded, but they produce ions in water. So I have this little diagram here to remind you that ionic and covalent, as it seems kind of black and white in terms of the bonding, is really a spectrum. There's different levels of covalent bonding, from nonpolar to polar. And then there's this area right here where we can have a covalent bonded substance that is almost over the line of electronegativity differences into ionic, where it might act kind of ionic, but it's technically still covalent. And that's really where our acids tend to lie. So if we think of these kind of like ionic, we are going to be cross-dropping reducing charges when we write our formulas. But all of these acids are going to have H plus in place of the metal ion. All acids start with H's. So they're held together by covalent bonds because they are all nonmetals, but they have that H plus ion at the beginning. Now, naming acids is really kind of the first hurdle, because naming acids is going to help us with formula writing. We're going to have to decode the names to be able to write the formulas. And much like with our ionic compounds, there's 2 big groups of acids, and the first one is binary, when the H, that is always at the beginning of our acid, is connected to a single element. And so just one other element there with our H. Now, all binary acids are going to start their name with hydro, and then the name is going to end with ic. So you'll notice here when I have chlorine, and just single plain little chlorine with our hydrogen, then this is hydrochloric acid. When it's sulfur there, it's hydrosulfuric acid. None of these numbers, or the lack of numbers, come into play in the name. It's just hydro, element name, root, ic acid. Generally takes the first syllable, but of course sulfur is weird and they took 2. If you wrote hydrosulfic acid, a chemist would understand what you're meaning and implying there. But once again, keep in mind, naming is not going to be its own singly identified problem. So you mostly need to be able to recognize and be fluent to be able to read questions, understand what they're asking, and find the compounds they're talking about. Now, the other type of acids are sometimes called oxyacids, but these are the acids that have a polyatomic group with their H. And because those polyatomics tend to have oxygen in them, that's why they're called oxyacids. And so the thing I actually remember, jumping back to binary, is this hydro is used in our binary acids when there's no O, because these are not oxyacids. So hydro only if there's no O in that formula. You can remember hydro with binary, it just doesn't rhyme, it doesn't go together as well, in my opinion. Now, with those polyatomic groups, there are still kind of 2 major groups of them. And so all of these are polyatomic acids, oxyacids, but the first type are the type that have a polyatomic that ends in 8 in them. If this is a polyatomic that ends in 8, then the name of that acid is going to get changed. You take off the 8 and change it to ic. And these don't have hydro at the beginning because these are going to have oxygen in them. So sulfate will turn into sulfuric acid. We just take off the 8, add the ic, add the word acid, of course, at the end. Nitrate, take off the 8, make it an ic, nitric acid. The other type of polyatomics are the ones that end in ite. If the polyatomic's name ends in ite, then the acid name with that polyatomic is going to get changed to us. So sulfite changes to sulfur-us, nitrite, nitrous. So I have this little silly saying, but it's stuck in my head since I was in high school. I ate a humongous bite. And it's just to help you remember that connection between these endings. Ick goes with ate, and then our us goes with ite. So you can always make the right change to the right polyatomic there. So this is kind of my summary if I were to put it all together with just kind of a formula for how to fill in the different acids' name. If it's binary, it's hydro something ic acid. If it's an oxy acid, we have to tell which the polyatomic is. You got to look at that formula, figure out if it's ate or ite version of that polyatomic, and then you take that root name of the polyatomic, change it to either ic or us, and of course add the word acid. So if you want to make this note up in the corner or off to the side someplace, you can. And I'm going to use that to help us when we're writing our formulas and names. But here with acid formulas, like I already kind of mentioned, the first step is going to be to decode the name. Figure out what is the thing with the H, because all our acid formulas are going to start with H. So if we see a name that has hydro in it, we know it's just a single element, and we can look at like hydrophosphoric acid. Oh, that's just phosphorus with H. If it doesn't have hydro, we got something like phosphoric acid, I'm going to go find phosphate. Phosphorus, I find phosphite. So you have to kind of understand the names to be able to decode them, see what the piece is with that H. And then you're going to cross-drop reduce with the H. But really, because H is a +1, let me use a real pen here. Whatever it is with your H, I'll just call that X. If that's a +2, then that formula is going to be H2X. The 1 is never going to get written down, so the 1 never really has to cross over. So all you've got to focus on is finding the thing that's with the H and its charge. Whatever that charge is going to be how many H's you have there. So let's do a few examples. And let's start with names, because that's such a key skill here. So here we have some O's, so our name is not going to start with hydro. The root name is just going to start with, what is the name of PO3? Well, that is phosphite if you check your polyatomic list. And since that's phosphite, we're going to change ite to us. So phos for us. And if you're like phosphorus acid, because you're like, where did that extra syllable come from? Scientists decided to add an extra syllable to some of these because it just sounded weird to say phosphorus, I suppose. But I would never count that wrong. Everyone will know what you're talking about there. With this next one, also not going to start with hydro because we've got some O's there. It's not binary. So we've got to figure out what is the name of this CO3 group, which is carbonate. Since that's changing, that's an 8, that's going to change to ic, so that's going to be carbonic acid. Our last formula down here is going to start with hydro in its name because there's no O's. It's just binary acid. So hydro, the middle of our name, the root of this name is going to be this element's name, phosphorus. And instead of that us ending, we change it to ic. All of our binary acids end with ic. So hydrophosphoric acid is its name. Now, writing formulas. If I see hydro here at the beginning, well, really, I know that all acids start with hydrogen. But hydro at the beginning means there's just one element with that hydrogen. And so if this is hydronitric acid, nitrogen is that element. And nitrogen's charge is a -3, which means our formula is going to be H3N. This is a nitric acid. There's no hydro there, but the names still start, the formula still always will start with an H because it's an acid. But if this is nitric acid, this is a polyatomic, and that ic ending there means that that's the 8 version of our polyatomic. So if we go look at nitrate, That's NO3 with a -1 charge, so that's just HNO3. The -1 technically crosses over, but it cancels out with that +1 immediately. Chlorous acid starts with H. Even though there's no hydro at the beginning of the name doesn't tell us whether it starts with H or not. Hydro just means there's no O's, that it's binary. So chlorous acid, us came from the ite version. So chlorite is ClO2 -1, which means this is HClO2. So that is the last of the review naming. We do have one more type of naming we're going to do, and this is really just ionic with a twist, and I left it to last just because it's pretty simple, straightforward, but it is something you're going to see in AP occasionally, and I don't want it to throw you off. There are these compounds called hydrates, and they have water as part of the crystal structure. They're like a sponge. They hold water. It actually helps stabilize the molecule by, filling in some of those empty spaces. But what it comes down to is in the name of a hydrate, they use prefixes, just like covalent compounds did, to denote the number of water molecules that they tend to absorb and hold within themselves. So because water is part of the structure, it becomes part of the name. These are ionic compounds. So the first part of the name is going to be normal ionic stuff, and then you're going to add this prefix, hexa, deca, whatever, for how many waters you got, and the word hydrate all together there. So here you can see CuSO4 is copper 2 sulfate, and then because there's 5 waters, we call it pentahydrate. So if we're looking at the names first, turning them into formulas, then cobalt 2 chloride is going to have cobalt with a +2 charge because of this 2 here. Chloride is a -1, so cobalt 2 chloride is CoCl2. And in this formula, we're going to put a dot because this isn't part of the crystal, it's just part of the kind of structure within the crystal. So it's not going to be technically changing that cobalt chloride formula. And then hexa means 6. So we've got 6 water molecules with it. That's our cobalt 2 chloride hexahydrate. Aluminum sulfate is going to be aluminum +3. Sulfate is a special group, but just write the formula the same as we would otherwise. Cross drop reduce, the 2 comes over. The SO4 has to be put in parentheses because that 3 comes over. So we've got our aluminum sulfate now. And then we've got decahydrate, which means that's going to be with 10 waters. Decoding these, right in the name, remember ionic compounds don't use prefixes in the name of that ionic part. We're going to use a prefix only for the water part. So Ba is barium, Cl becomes chloride. Why my eyes are struggling here. And then we've got 2 waters. 2 is di, and water is hydrate. Cu2S, that's copper and sulfur. Copper is a transition metal, so we're going to have to find that Roman numeral here in a moment, but we might as well finish. 9 is nona, so that's nonahydrate. Looking back at this, sulfur has a -2 charge, and I have 2 coppers that when added together cancel out that -2 charge. So each of those coppers has to have an individual oxidation number, an individual charge of +1. So that's copper 1 sulfide, nonahydrate. Hopefully that's not too bad. It's the only part that should be completely new to you, but it kind of combines pieces of things we've already touched on. So that next piece of paper in your packet is just kind of a summary of everything. It's got everything but our hydrates in them, so that if you need to, figure out how to write a name or a formula on this next page where everything's mixed up, start at the top. Start by looking at what type of elements you've got. I'm keeping in mind acids, might look like it's molecular, might look like it's nonmetals only, but acids always start with H in their formula, and their names have the word acid in them, so that's pretty straightforward. Once you know what type of compound you've got, then you can go through the flowchart, kind of ask yourself these questions, and hopefully use it to help you get there to your answers. But this is the last bit of individual practice that I want you to try out. Try writing some of these names and formulas here on page 13, and I would like you, at least in that top part, to write the type of compound. You can just put an I, C, and A for ionic, covalent, acid, or H for hydrate, I suppose. I don't mind if you call hydrates ionic, because they are mostly ionic. But just practice identifying that type, because that should always be your first step before you have to write that name. I didn't really include a specific spot for it. I didn't write the word type again at the bottom, but I still think it could help you to find that type before you try and write that formula, because there's different steps to writing them.